So I'm going to talk about statistical estimation at this point in time. This is where if we know some information about a sample, then we can actually make some estimates about our actual population. So the first section here that I'm going to talk about, so I'm going to do this in a segment of, I believe, 4 videos. So the first one is going to be estimating our population mean when we know what the population standard deviation is, or we can guess at what that is. So, like I said, we have a random sample of n items or n values drawn from a population that has a whole bunch. We know the samples or the population standard deviation. Like that is something we've known, usually from historical data or something like that. We just may not be as sure about the actual mean right at this time. If the X distribution is normal, then we can use any sample size. However, if we don't know what the distribution is, we need a sample size of at least 30. And if it's really not mound shaped or skewed one way or another, we could even use bigger sample sizes like 50 or 100. All right, so kind of a definition here, point estimate. The sample mean would be a point estimate for our population mean. We're using that as a single data point to kind of estimate stuff about the population. So that's kind of a vocab thing. And then our margin of error would be how different is our actual mean to the sample mean. So technically speaking, there should be a bar above this. So what is the difference between our X bar and our mu? So remember, this deals with our sample and this deals with the population. Well, we can estimate this within specific confidences. And our confidence comes from that area of our normal scores, our standard score table or Z table. And it's going to be in a middle area there. So we know if we're within one standard deviation, our confidence would be 68%. We can roughly say 68% of the data falls within one standard deviation. But now we'll be going backwards. What if I want to come up with like a 90% confidence level? So I'd want this area to be 90%, and I'd figure out what these are. Thankfully for us, and that's what this is saying, thankfully for us, we've got a table that already sets up and tells us what those values are. So a 90% confidence level, those values would be plus or minus 0.1645. That's going to be our Z, our critical Z value. So this table is in our book of tables and stuff. And so you might keep that handy. And if you have your textbook, a lot of times this is inside a cover of your textbook. So for my classes, it's inside the front cover of our textbook. But you could also find this probably on the internet at any point in time. So you could find critical Z value table and you'd probably find this table. All right, and once again, that's telling us what's going on in here. So lots of different views. All right, to determine our error. So we can, with 90% certainty, guess what that error is going to be. And this is our formula for doing that. We'll take our critical value that we got from that table and take it times the population standard deviation divided by the square root of whatever our sample size is. This formula is huge. Make sure you have this formula somewhere, okay? And then once we have that formula, we will add and subtract it from our sample mean. And that gives us our interval for which things are going to fall. That gives us our 90% or 80% or whatever our interval it is that we're looking for. And then here's a table that walks you through all those little steps. Now, I want to point out to all of you that you do have a table of formulas. So within our formulas here, if you go to chapter 8, because that's what chapter we're on in my stats class, we have confidence intervals. So if we're trying to find the confidence interval for the mean, here's what we would do. And then it's whether we know or don't know that population standard deviation. So what I'm talking about in this first video is this one right here, and there's that formula we just talked about. So, and I will put this on Classroom again in case you can't find it. All right, so what does it mean? And I'm going to use a 90% confidence interval for our example here, but what does that mean that we have a 90% interval for the samples of the same size? So what does that mean? It means if I were to take 10 samples of the exact same size, of whatever it is I'm testing, that means 9 out of the 10 of those samples would have their mean that fall within our interval. So our interval is denoted by these blue lines, depending on what it is that we're looking at and what our different numbers are that go into it. Notice this mu, our population mean, hits every blue line except for one. So 9 out of 10 times, we are within our range that we're looking at. And that's what it means to be a 90% confidence interval. So 90% of the time, our mean is going to be within that range. All right, and we'll come back to this. This is if we don't know our sample size and we want to kind of estimate what that would be. So let's do an example here. 30 small communities in Connecticut with a population near 10,000 each gave an average of reported cases of larceny per year. Assume that sigma is known to be 42.46 cases. So I'm actually going to mark that. So sigma is 42. So 42.6. Find a 90% confidence interval. 90% confidence interval. So for the population mean, and what is the margin of error? So to be able to find that confidence interval, we need to know that margin of error. So I'm going to pull this back over here real fast. Here's our formula for that. And this is going to be our margin of error. We have to know that before we can find the interval. So our margin of error formula, I'm going to put that over on this side, is going to be E equals our critical value times sigma over the square root of n. Okay. We got to figure out some different things here. So 30 small communities. So that's going to tell us our n. Here's our sigma. The ZC is what we need to find now. If we want a 90% confidence interval, that means we need to go back to this table, back here ways, and find 90%. So here's our ZC, is 1.645. Sorry, bear with me a second here. So our ZC is 1.645. So now we can find this margin of error. So our margin of error is going to be E equals 1.645 times 42.6 divided by the square root of 30. And this is going to be an estimation, and I would say let's estimate it to, we'll do 2 decimal locations. That seems like a good thing here. So let's, and I'll give you a moment to do that calculation. All right, so this value ended up being 12.79. Lost my pen. So we're going to estimate, so 12.79. So that is our E, that is our margin of error. So now we're going to make a 90% confidence interval. So what does that mean? It means we're going to take X bar minus our E, and then X bar plus our E. Well, our X bar is up here. That should have a bar. So our X bar is that number right there. So we are going to do 138.5 minus 12.79, and then 138.5 plus 12.79. All right, this would end up being 151.29, and if you want to go to 3, you could. And use, this one's going to end up being, sorry, I have those backwards. Type the wrong thing on accident. So let's move that around. I apologize for that. This one will be 125.71. And this one will be the 151.29. So 90% confidence that the population mean will be between 126 and 151 cases of larceny per year. That's kind of what we're going to estimate, and that's what that 90% confidence interval is. So now let's do a 99% confidence interval. So my question is, do you think it's going to get bigger or shorter? our interval to be 99%. Think about it this way: 90% was in the middle, 99% means we got to spread that interval out. So these numbers should be further apart. To be 99% confidence, we have to allow for more room for error. So our error formula is actually exactly the same, except for we have to find a new ZC. So ZC, so let's go back up here. We're looking for 99%, which would be 2.58. So our ZC here is 2.58. So 2.58 times 42.6 all over the square root of 30. All right, that makes our margin of error about 20.07. We could say 20.1, that might actually be a little bit nicer. So once again, we take our mean, so 138.5 minus 20.1, and our mean plus 20.1. So we'll have 118.4 to 158.6. So our 99% confidence interval, notice our interval is much wider. Because we want to be more confident, we had to open that up a little bit. Think of it as confidence in making a shot, or like shooting a bow and arrow. Okay? If our bullseye is very tiny, our confidence is less than if our bullseye was really big. We'd have more confidence that we'd hit somewhere in that bullseye. So we got to have a bigger space, bigger interval if we want a higher confidence level. All right, so part C is now we want to find a sample size. Let's hide this so we can see what we're doing. So find the sample size necessary for a 95% confidence level with a maximal error of 10.6 for the number of reported cases of larceny per year. Okay, notice now we are given the E. We are given the E. We don't know the sample size, but we do know we want a 95% confidence interval. So that comes back to this formula right here. So this is our sample size when we need to estimate. So we'll have ZC times sigma divided by our error, and then we'll square that. And we always round up to the next integer. Let's give us a little space here. Okay. So n equals ZC times sigma divided by our E and the square of that. All right, 95% confidence interval is 1.96. So we're going to have 1.96. We know this is still 42.6. That didn't change. But now our margin of error, we want it to be 10.6. So we're going to do this multiplication, square it, and figure out what that is. So 1.96 times 42.6 and divided that by 10.6. And once that's squared, you get 62.05. And remember what I said, always round up to the next integer. So our sample size, even though this is so close to 62 exactly, I mean, it's literally 62.05. We always round it up. All right. So we need 63 is our sample size that we would need to be within that range at a 95% confidence level. All right, so this is how we do confidence intervals when we know the population standard deviation. Stay tuned for what happens when we don't know it.